20th International Physics Olympiad. Year 1989. IPHO. I offer private tutoring for preparation for physics Olympiads. I currently have openings. Write to me if you are interested. There is a discount for group lessons. My email is fred1996@hotmail.com. Problem 3. Proton microscope. The solution to this problem can be found at the link in the description under this video. The problem concerns investigation of transforming the electron microscope with magnetic guiding of the electron beam, which is accelerated with the potential difference, U, equal 511 keV into a proton microscope, in which the proton beam is accelerated with the potential difference, U. For this purpose, solve the following two questions. Question A. An electron, after leaving a device, which accelerated it with the potential difference, U, falls into a region with an inhomogeneous field, B, generated with a system of stationary coils L1, L2, etc. till Ln. The known currents in the coils are I1, I2, etc. till In, respectively. What should the currents I1', 2', etc. till In' in the coils L1, L2, etc. till Ln be, in order to guide the proton, initially accelerated with the potential difference, U, along the same trajectory and in the same direction as that of the electron? Hint: the problem can be solved by finding a condition under which the equation describing the trajectory is the same in both cases. It may be helpful to use the relation 1. Question B. How many times would the resolving power of the above microscope increase or decrease if the electron beam were replaced with the proton beam? Assume that the resolving power of the microscope, that is the smallest distance between two-point objects whose circular images can be just separated, depends only on the wave properties of the particles. Assume that the velocities of the electrons and protons before their acceleration are zero, and that there is no interaction between own magnetic moment of either electrons or protons and the magnetic field. Assume also that the electromagnetic radiation emitted by the moving particles can be neglected. Note, very often physicists use 1 electron volt, and its derivatives such as 1 kilo electron volt or 1 mega electron volt, as a unit of energy. 1 electron volt is the energy gained by the electron that passed the potential difference equal to 1 volt. Perform the calculations assuming the following data. Rest energy of electron is 511 kilo electron volt. Rest energy of proton is 938 mega electron volt. Solution to problem 3. Solution to part A. At the beginning one should notice that the kinetic energy of the electron accelerated, with the potential difference U equals 511 kV equals to its rest energy E0. Therefore, at least in the case of the electron, the laws of the classical physics cannot be applied. It is necessary to use relativistic laws. The relativistic equation of motion of a particle with the charge E in the magnetic field B has the following form. Expression 2, where P equals m0 gamma v denotes the momentum of the particle as a vector and Fl equals Ross product EV by B. Expression 3 is the Lorentz force. Its value is EVB and its direction is determined with the right-hand rule. m0 denotes the rest mass of the particle and v denotes the velocity of the particle. The quantity gamma is given by the formula for, the Lorentz force Fl is perpendicular to the velocity v of the particle and to its momentum P equals m0 gamma v. Hence, dot product Fl by equals dot product Fl by P equals 0. Expression 5. Multiplying the equation of motion by P and making use of the hint given in the text of the problem, we get, expression 6, it means that the value of the particle momentum, and the value of the velocity, is constant, during the motion. P equals m0 v gamma is constant and v equals constant, the same result can be obtained without any formulae in the following way. The Lorentz force Fl is perpendicular to the velocity v and to the momentum p as p equals m0 gamma v and, as a consequence, to the trajectory of the particle. Therefore, there is no force that could change the component of the momentum tangent to the trajectory. Thus, this component, whose value is equal to the length of p, should be constant. The same refers to the component of the velocity tangent to the trajectory as p equals m0 gamma v. Let S denotes the path passed by the particle along the trajectory. From the definition of the velocity, we have delta S over delta t equals v, equation 7. Using this formula, we can rewrite the equation of motion as 8 and 9. Dividing this equation by p and making use of the fact that p is constant, we obtain 10 and hence 11. Where t is the versor, unit vector tangent to the trajectory. The above equation is exactly the same for both electrons and protons if and only if the vector quantity 12 is the same in both cases. Denoting corresponding quantities for protons with the same symbols as for the electrons. But with primes, one gets that the condition, under which both electrons and protons can move along the same trajectory, is equivalent to the equality 13. However, the Lorentz force is proportional to the value of the velocity of the particle, and the directions of any two vectors of the following three, t or v, fl, b, determine the direction of the third of them, right-hand rule. Therefore, the above condition can be written in the form of 14. Hence we have 15. This means that at any point the direction of the field, b, should be conserved, its orientation should be changed into the opposite one, and the value of the field should be multiplied by the same factor p' over p. The magnetic field, b, is a vector sum of the magnetic fields of the coils that are arbitrarily distributed in the space. Therefore, each of this field should be scaled with the same factor negative p' over p. However, the magnetic field of any coil is proportional to the current flowing in it. This means that the required scaling of the fields can only be achieved by the scaling of all the currents with the same factor negative p' over p, equation 16. Now we shall determine the ratio p' over p. The kinetic energies of the particles in both cases are the same, they are equal to expression 17 which is 511 keV. The general relativistic relation between the total energy E of the particle with the rest energy E0 and its momentum p has the form 18. Where c denotes the velocity of light. The total energy of considered particles is equal to the sum of their rest and kinetic energies. Expression 19. Using these formulae and knowing that in our case Ek equals Eu equals Ee, we determine the momenta of the electrons, p, and the protons, p'. We get for electrons 20 and 21. And for protons 22 and 23. Hence p' over p equals about 35. 0, expression 24. And In' equals negative 35.0 In, expression 25. It is worthwhile to notice that our protons are almost classical, because their kinetic energy Ek equals Ee is small compared to the proton rest energy Ep. Thus, one can expect that the momentum of the proton can be determined, with a good accuracy, from the classical considerations. We have formulae 26 and 27. On the other hand, the momentum of the proton determined from the relativistic formulae can be written in a simpler form since Ep over Ee much greater than 1. We get p' approximately equals expression 28. In accordance with our expectations, we have obtained the same result as above, that was solution to part A. Solution to part B. The resolving power of the microscope, in the meaning mentioned in the text of the problem, is proportional to the wavelength, in our case to the length of the de Broglie wave. Lambda equals h over p, expression 29. where h denotes the Planck constant and p is the momentum of the particle. We see that lambda is inversely proportional to the momentum of the particle. Therefore, after replacing the electron beam with the proton beam, the resolving power will be changed by the factor p over p prime, which is approximately 1 over 35. It means that our proton microscope would allow observation of the objects about 35 times smaller than the electron microscope. Remarks and typical mistakes in the pupil's solutions. Some of the participants tried to solve the problem by using laws of classical mechanics only. Of course, this approach was entirely wrong. Some students tried to find the required condition by equating accelerations of particles in both cases. They understood the acceleration of the particle as a ratio of the force acting on the particle to the relativistic mass of the particle. This approach is incorrect. First, in relativistic physics, the relationship between force and acceleration is more complicated. It deals with not one relativistic mass, but with two relativistic masses, transverse and longitudinal. Secondly, identity of trajectories need not require equality of accelerations. The actual condition, that is the identity of E, B, over P in both cases, can be obtained from the following two requirements. First, in any given point of the trajectory, the curvature should be the same in both cases. Second, in the vicinity of any given point, the plane containing a small arc of the trajectory should be oriented in space in both cases in the same way. Most of the students followed the approach described just above. Unfortunately, many forgot about the second requirement. They neglected the vector character of the quantity EB over P. That was solution to part B. And we finished discussion to problem 3.